second day of this final workshop. I'm glad to announce first talk of today. The talk of Adam Parusinski, Université Côte, who will talk about arc-wise analytic stratification.
Okay. Do you hear me?
Yeah. Yes, we hear you well.
Okay. If there is any problem with image or the sound, just let me know. So thank you very much for invitation, and I feel very sorry that I cannot be in Toronto with you, but I brought here a souvenir from Toronto. It's a Fields Institute mug with my name on it. So, and it's Yimu Yin is in my office and sending all of you his best regards. So the subject is arc-wise analytic stratification, and actually arc-wise analytic triviality. And this is a subject I worked a few years ago with Laurențiu Paunescu from Sydney. So I'm going to introduce it today, and I think conjecturally it can be related to some work on Tame and non-Archimedean geometry. So you can see on the screen the coordinates of my paper. I'm going to write down my talk. Coordinates of my paper, but there is a new preprint, but Pablo Cubides-Kovacis and Immanuel Chalupcho, arc-wise analytic T stratifications available in my archive, and I do not say that it's the same subject. I think it's at the moment the relations are very loose, in my opinion, but it maybe these arc-wise analytic stratifications and trivialities can be useful in Tame and also in non-Archimedean geometry. So let me start with a few definitions. So general setup. Oh, sorry. So the setup is actually we work in four categories. So the field is either standard real numbers or complex numbers, and I'm going to work either with algebraic varieties or K-analytic spaces or sets, subsets of affine space. So I have to change my. So I will start already with a theorem. So if we have an algebraic subset, then there exists an algebraic stratification of X admitting regular arc-wise analytic trivialization. I'm going to write it down. Trivializations along each stratum. And actually, we are going to do it as usually one does, a little bit differently. We are going to stratify the whole space in such a way that X is a union of strata. Of course, in the analytic case, the result is local. So I'm going to explain all these strange words, regular, arcwise, analytic, trivialization. But let me tell you that probably you are accustomed to stratification theory through Whitney conditions or some other conditions, how the strata glue together. And this, here the philosophy is a little bit different. So instead of proving those conditions and then to construct trivializations, you start with the trivializations. So now I'm going to explain the words, starting by what does it mean algebraic stratification. This is easy. This is actually a filtration for me, which means that I start with our space Kn, which I'm going to denote Xn, and then I filter it by algebraic sets. I use the same letter X, sorry. In such a way that all Xi are algebraic, and Xi minus Xi minus 1, it's just a non-singular pure dimensional of pure dimension I, or it could be empty, but this in this setup happens very rarely. So this is the result. And let me just recall, before I recall what does mean arcwise analytic, let me just recall what is a trivialization. So let me make a simple picture. So you have your set. And you fix a point on a stratum. And then suppose that you have a projection on the stratum. So you take a small neighborhood of the stratum, which I'm going to denote by T, and it would serve as a parameter space. So that's why T. It would be, sorry, it's a little bit different. So I have my neighborhood. So this is neighborhood of P naught. And we have a projection, which is in the category meaning that it's, for instance, analytic or Nash in the algebraic case. So, for instance, a special fiber over P naught, it's a kind of normal sections or transverse section. And you would like to trivialize it. So this section becomes constant in a family. So this I will call and the trivialization big phi. So it's phi goes from T times its value is omega. And it's preserves a set or a sets, whatever we would like to trivialize. So this family on the left is constant. Of course, what I'm going to do later, I'm going to simplify it, the picture. Yes. I'm going actually to assume that my set on the right, omega, lives in T times K n minus the dimension. Just choosing local coordinates. This could be analytic local coordinates, formal local coordinates, or Nash, which means analytic, semi-algebraic, whatever you prefer. So the picture will look mostly like the same trivial family on the left. And on the right will be the family of germs, but this family will be not trivial. We'll have the same central section, but then it would be more like this. This is just to simplify the picture. So this is our omega 0. So this is always possible to do by a local change of coordinates, which should be the class. Like analytic is okay. Because, okay. And now we would like to ask this trivialization to have special properties. And already the first one is an interesting one. It is phi is real, and this usually people do not say arc-analytic. Whenever I say arc-analytic, it means real analytic, which means that for every arc, to our space, let's say or arcgerm phi composed with delta is arc-analytic. So I is -1, or it's an open, or minus epsilon, epsilon, because it's a germ, is analytic. But we have better property, which is called arcwise analytic. Because you see, phi depends on two variables. One variable which is in the parameter space, so I treat T, big T as a parameter space, and the other variable is in this section, special section. So when you move T, the section changes. So we want that phi to be K analytic in T, and of course, real analytic in Z. Which simply means that locally you can write it down if you want as a convergent power series, but some variables are considered complex and some variables are considered real. Okay. What we want also that of course that phi is a homomorphism, which I didn't say, but it was always trivialization means this. That's a homomorphism, but this homomorphism should be in the category subanalytic or semi-algebraic in the algebraic case. But semi-algebraic means real semi-algebraic. There is no complex structure here. And these are the important properties. Oh, sorry, I forgot one more important property, that the inverse of phi is also arc-analytic. Not arcwise analytic, arc-analytic. So in particular, phi gives bijection between real analytic arcs. But it's even better that it's with respect to T is in the complex case is complex analytic, and not only on the arcs. With respect to T, it's a global dependence. So maybe this theorem which I stated was used to show Whitney's conjecture, which I'm not going to repeat today because it's not my purpose, but it simply means that when you take fix Z and take the image of phi T Z naught, or you fix Z and you move T, then you get in the complex case, you get a complex subvariety. Complex analytic subvariety is the image, and the whole neighborhood is fibered by such subvarieties. So this is what is arcwise analytic trivialization, but there was one more word which was regular. And this regularity is important actually also for the conjecture. So it simply means that if I write my phi of tz as t, so you preserve the sections, and psi, capital psi of tz. So you look how your sections are moving. On the left hand side, the sections are constant. On the on the right hand side, they evolve, they change, deform. So this is this second coordinate, big psi. You would like the following property, that the distance, if you suppose that you work on the around the origin, I'm not going to simplify it. So the distance of how this point is evolved with respect to the origin, with respect to t axis, if you want, does not move a lot, which simply means that up to a constant psi of t0z, and actually psi of t0z, you can suppose that it's z, it means it, sorry, so this is t0. It means that on the level t0, you have exactly the same section, both ways. So regularity means that the distance to the stratum by this stratification is the magnitude of the distance is preserved. It's as simply like this, but it's important. And before I explain why, let me just put one proposition which probably would be obvious for you, because you are the experts in proposition, that phi is regular at some point if and only if for every real analytic arc germ, say, when you write this function, which is now analytic, both in S, in T, this was the condition. When you expand it with respect to the power of S, and d k naught is the first non-identically zero coefficient. Yeah, so we have this convergent power series in T and S. This leading coefficient does not vanish. So this is fairly easy to show. And now, why this is important? Okay, are there any questions? Okay. Do you hear me?
Yes.
Okay. Okay. So it's now I'm going to explain why it is important, because it's some remarks. Remarks which are so when you work with stratification, usually you want regularity conditions in standard, like Whitney conditions, for instance. So if you have a stratification admits this arcwise analytic trivialization, then it satisfies a condition of Whitney, which is very weak result, a condition of Whitney. I will write it arc A. This is how we wrote it, implies A. But if it satisfies a regular, so it's important that I added here regular. Then we have W condition of Verdier, which of course in ominimal setup implies B of Whitney. So, and this was what Whitney asked in his conjecture, whether there exists in complex case such a vibration by complex analytic submanifolds, which are our leaves of trivializations, which also gives his conditions, A and B. I don't know whether I have really time to prove it, but the proof is very nice and very short. So I will just sketch it. So if we compute this d phi dt, so phi was, I'm going to repeat here, given by this formula. So it's the sum d dk dt and of course this is smaller or equal up to a constant as the sum of dk S of k, because dk does not vanish. This was a regularity condition. And if you understand what I wrote exactly something which implies W condition because W conditions means that if you take the sequence of point in one stratum, which tends to a point on a smaller stratum, then the angle of tangent spaces here would be 0, goes to 0, which means more or less that the limit of tangents to the big stratum contains the tangent to small stratum, even if this limit does not exist. But it exists along real analytic arc. it's enough to check it along real analytic arc, and along real analytic arc, it follows easily from this property. Because actually this, maybe I will make another picture, sorry. Actually this, so when you have this family, which is not necessarily trivial, and I take my curve, I can take its, let it flow. So I can take phi of t, z of s. And this, I get a kind of a wing as an image. And this wing will be a real analytic set, which would be by this property, which I explain, regularity C1 manifold. And this is W condition. Okay. I do not have much time, so I'm going just orally say two things that you can do the same for a function, and then you can stratify in such a way that you have the property for a function, like for a polynomial. So you have the property that df so you can handle finitely many functions as well and have this property. This implies, of course, that the zero set of f is preserved by phi, but this is some kind of local property which implies a f condition of Tame, so it's another regularity condition. Another short remark, it's the following. Okay. So we can trivialize, we can find always stratification which trivializes in a very strange way. With respect to parameters, everything is very nice, which means analytic. But with respect to transverse variables, where we are really interested in, it's only arc analytic, analytic on real analytic arcs. The answer is that you cannot expect more, because there is Ehresmann theorem. Oh, it's 1s. And in particular, you can apply Ehresmann to complex analytic. So this will be the proper holomorphic complex analytic map of analytic manifolds. So what you can prove, and it's not so difficult, that for every point in the base, B like base, there is a neighborhood and a trivialization yes, like this, which is holomorphic in T, and real analytic in Z. Yep. This is in the case of no singularities. But of course, you cannot expect complex analytic in because of a rigidity. You have rigidity of complex structures, and you can do nothing about it. So this result is not difficult. You can find it in the book of Claire Voisin, and she quotes for the proof Demailly, Jean-Pierre Demailly. So our theorem is kind of a singular version. So singularity forces the change of real analytic in the transverse section variable to real arc analytic. Okay. Now I would like to, are there any questions? Because I would like to come to a little bit more to the subject of this of this conference. So how it can be related to some Tame geometry? Okay, of course, it's a easy observation is that in the semi-algebraic setup, what you can do, you can always stratify with some kind of half arcwise analytic. Meaning that you should consider only arcs which are defined for positive S. It's already quite strong trivialization. The proof applies as well to semi-analytic. I don't know whether to sub-analytic, so let me put it as an open problem. So this is easy observation. But really important problem is when you study the spaces of arcs, you would like to take the truncations, and you would like, when you have trivialization which gives you bijection of arcs, you would like this trivialization to be to trivialize the spaces of truncations. So an open problem is the following. So X in Kn algebraic is the stratification with local trivializations arcwise analytic and Lipschitz and by Lipschitz. which means that phi preserves order of contact between real analytic arcs. And it's strangely enough, you can construct such a stratification which has trivializations which are arc-wise analytic. That's our theorem. And you can construct such a trivializations which are by Lipschitz. But I don't know how to do it with one trivialization. So these two one I think it's an important important open problem, and there are some works, as I mentioned, in this direction, which include also work on non-Archimedean fields, because it's as you see, we have arcs, we have Puiseux series, so we have some translations to non-Archimedean fields. Okay, so maybe let me finish with the following observation and remark. So there is this work of Chalupchok and Kovacic-Chalupchok. So there is this notion of T stratification. And T squared stratification. Yimu knows what it is, yes? and also arc-wise analytic stratification in a way. Stratification. So maybe I will put here Chalupchok C and but as I said, it's loosely related. So the construction is more or less like this, that I'm not going to talk about it because I don't have time and it's a subject for another talk, but the construction is the following, that if you would like to trivialize our singularity, you choose an arc and you choose let's say that this arc is inside, sorry, that this arc is inside our set. Of course, the dimension is here very too small for a good picture. And then you can find a neighborhood such that in this that you can straighten in a way this neighborhood by a map which is called by them rhizometry. And you straighten this neighborhood. So it's our, and this is defined in the non-Archimedean setup, but it's in particular that they are able to prove that it's this arc-wise analytic stratification exists in some setups, implies T2, And this implies Lipschitz of Mostowski stratification, which is generalization of Verdier condition. But the problem is that this is very local. This straightening is very local. It depends on the ball, on the curve. It does not come from the global in the sense in the neighborhood trivialization. And actually, it's very difficult to talk about trivialization in non-Archimedean setup. It's actually rather you want to prove the properties on the tangent spaces, like Verdier, which I mentioned today, or like much more complicated this Lipschitz conditions of Tadeusz Mostowski. So let me finish.
Thank you. Are there any questions or comments?